So I did say I won't be doing any videos related on learning something new, but this is not learning something new. It's just me clarifying what was going on in a question that I got in a test. So Sunday, the last Sunday, I gave a test and I got this question. So here's the thing: you got an electron inside this space. So it's actually supposed to be 3D space, but then just think of it as 1D space or whatever. And yeah, so think of the electron as a planar, um what we call it, a planar wave, right? So plane wave, yeah. And the electron is going back and forth. So first it's like here, and then it goes over here, and then it comes back and whatever. All right. And because it's a wave, you can use wave particle duality to say that the energy of this system, right, it is it can only take some discrete values. So they want us to figure out what is the ground state energy of this thing, right? So how do you do this thing? The easiest way of doing this is, of course, to assume that um, that this length is actually an integral multiple of lambda upon 2. Why am I doing that? Because the usual assumptions that you make for wave particle duality is that the wave function, which is called phi, this is equal to some amplitude at some point, right? So yeah, well, we don't know what that thing is, which called as a of x. So because yeah, yz symmetry, so there's like only the only variable that we need to look out for is the x, um, right? So we only need to worry about the x coordinate of our electron, right? So our phi is a of x. So a is just the amplitude, and then this times sine of omega. I know it's not actually supposed to be sine omega t, it's like e power I omega t, but then you take think of it as a phasor basically. So it still gives a real value and whatever. Or you could think of it as a complex value itself, but I don't like to think of it like that, because why? But yeah, so this is the thing. And then of course, like phi square is okay, actually not this thing, a square, right? So a square is related to probability, right? So it's the probability of finding the electron at that point. So that's the usual assumption that we make. Now the thing is, this particle is completely confined into this space, right? But that the wave function, it's supposed to be continuous. So it's supposed to be continuous throughout the 3D space, that I mean, like throughout the universe basically. So even though the particle is confined, it could go out. I mean, you could take the hypothetical scenario that it is in fact going out, and the probability of it going out would be zero, because of course, I mean, like we just said, it's confined to this space, so we know that in fact it doesn't go out. So the probability of it going out is zero. So what does it mean? That just means like phi is zero, or I should say a is zero. So a is zero at this point and at this point, right? um yeah, a is zero at that point and that point. And we know that uh, our a of x, that actually is of this form. We'll just say it's equal to, okay, I need another amplitude, which is, I'll just say a dash. Okay, so a dash of x, not x, now this is constant at this point, so it's a dash, which is actually a constant. And then you got, and you can figure that out. So what is this constant and all that stuff? Right, we don't do that. It's just like this thing times sine of uh, what was I doing, sine of kx plus phi, where k is of course just 2 pi upon the wavelength of our particle. So it's particle is just the electron. So you got this as our amplitude is a function of x. Now the thing is, at this particular point, because of continuity, a must be 0. So, and also at this point it should be 0. So if we just set our x-axis like this thing, so this is our origin and this is our x coordinate, right? And x equal to 0, it's 0. What does that mean? That phi must be 0 or something like 2 and pi. But yeah, just set it as 0 because we don't care. Even if it was 2n pi, just you could still write it like this thing, so a of x would still become this. Okay, and then at x is equal to L, so if this complete length is L, just a small L, because yeah, so at x equal to L, this would still be 0. So what that means is like L times k is n pi, right? So it's an integral multiple of pi, but then k is just this thing, so L times of this, that's equal to n pi. So that just means like L is equal to n lambda upon 2. This is well known, right? So basically the electron is kind of like a standing wave. Yeah, does that make sense? So this is just n lambda upon 2. But then remember what lambda is. So since we are dealing with our wave particle duality, we know that the lambda is just our de Broglie wavelength, which can be given as h upon p. So there we go, you can write it like this thing, n times the Planck's constant upon 2 times the momentum. So our momentum is just nh upon 2l, right? But we know that our kinetic energy, that's just equal to p square upon 2m, right? So like half mv square, but you can write it like this thing. It's very trivial, just do it by ourselves. And then this is going to be equal to n square h square upon 4l square, but then you got these things like 8l square m square. Oh, sorry, 8l square is just m, right? Yeah. So this is our kinetic energy. Now, yeah, I mean, this is our kinetic energy, and then at this particular point, we'll just assume our potential is 0, right? There is supposed to be more things going on than just the kinetic energy. There's also supposed to be the potential energy, but then we'll assume that potential throughout this space is just 0, and in this space it's supposed to be infinity, right? Yeah, I mean, I won't explain why that's happening, but one thing you can be certain of is that the potential in this region, you can assume that to be constant for this kind of thing, right? Yeah. So like, yeah, basically a particle in a box, isn't that right? So we got our kinetic energy, and this is basically just equal to the energy. So energy is given by this thing, n squared h squared upon 8l squared m, right? You can call this h squared upon 8l squared m as e naught, and then that's n squared, right? Or e1, because at n equal to 1 you usually have this energy. So this is the thing. So for n equal to 1 you will have e1, then n equal to 2 you will have like 4 e1, and so on. So that's the yeah, like this thing is our ground state energy. So this is our final answer. Oh, sorry, e1 is our final answer, right? It's just h squared upon 8l squared m, and there we go, that's it. All right, so I'll see you in the next video.